today we want to finish off the main theorem that concerns this discrete group theory, and it is called the great orthogonality theorem. In another book that I found, it is called wonderful orthogonality theorem. So it depends on whether you like got or what, you can call it what you like. So let us put down the various concepts we are dealing with. One is of irreducible representation. And we want to move towards what, and we have defined characters which are essentially traces of d alpha g. So the irreducible representation we will denote by d, and alpha is some kind of a label. Sometimes it is directly the dimension of the group, or sometimes something else that characterizes that. I'm sorry, alpha is either the dimension of the representation or something else that characterizes it, and the characters are traces of the matrices d alpha which represent elements G for G belonging to G. Okay. The representation is meant to be, as we have already said, with carrier space some linear vector space and d alpha are matrices. So in a representation it almost always means carrier space some vector space V and d alpha as linear operators. Now some people had a question last time at the end, because the idea of what is irreducible was not completely clear, and we had said something like if there is a invariant subspace, if a space breaks up into two subspaces which remain invariant, but the idea is of reducible versus irreducible. Is simply that if I have a matrix D which breaks up into block diagonal form, such that only these are non-zero and all these are 0. Okay. What this means is that in any basis we have constructed, or so any vector we take belonging to, this belongs to V, and if this matrix acts on that V, it is going to take the first few only into themselves. Those components will only be mapped into those components. The next few will only be mapped into themselves, and the last segment will be only mapped into itself. So those basis vectors will never be transformed into these basis vectors, or these will never be transformed into those. Okay. So each of these is called an irreducible subspace, or it's called invariant subspace. So these become all invariant subspaces. Of D for the time being. But the point is that if for the entire representation, for all G belonging to the group, if every single matrix D that represents them breaks up like this, then we have some redundancy, because we could have just looked at this last few components and we would have got a representation. We could have looked at this subspace and we would have got a representation. So the idea, this is called a reducible representation, and when you restrict yourself in such a way that there is no invariant subspace to it, then it is called irreducible. So just to repeat that or write it down a little bit, we just said that if it can very well happen that by accident one element happens to have some form like this, but if it happens for all the elements of G, then we call such a representation reducible. We will find that for a given group, the number of irreducible representations is also limited. You can't indefinitely keep finding newer and newer irreducible representation. If a newer representation you find, a larger one you find, it will be possible to break it up into the smaller ones, which are all irreps. So we will see that there is a limit. There are only finite number of irreps. Any larger rep will be reducible. Reducible into these. And we will find that the irreps actually act somewhat like a basis. You find any general large reducible representation, you can almost represent it like a linear combination of the smaller ones. The whole problem has been transferred to linear spaces now and to linear algebra, and lot of the powerful results that follow from linear algebra apply. And so we will find that there is almost like a the irreps almost form a basis. I am just writing sort of, because I do not see any theorem stated of that type, but the statements we will prove will convince you that this is what it means. In terms of which a general rep can be linearly formed. So, linearity is always a great thing because it keeps things simple. Can be linearly decomposed. So, that is the general idea. By the way, I finally discovered, I am sorry to say, everything is a journey, So, I have been teaching this course now for 3 years, but finally we did not have this course earlier in the department, we never taught it formally. Anyway, I finally latched on to a good book. It is rather comprehensive, it is a big fat book, but it is also free, put up by MIT, and I have put the link in the Moodle. This is a book by, it is actually written for condensed matter physics, but its first few chapters will be useful for us, and it goes by example. So, that is a very nice thing. So, any larger rep will be reducible. And of course, when I said larger, I meant larger than the largest irrep that exists. So, now we go back to what we were trying to do last time, which was first to prove Schur's lemma. So, we dive into a bit of mathematics for a while, and then we will come out and then prove this nice result that every irrep is linearly decomposable. And just to make the larger connection, the point is that if you have any vibrational modes of a molecule, then you can analyze them by their symmetry. The vibrations essentially fall into some representation of the symmetry group of the molecule, and if you have arbitrary vibration, then you can decompose it linearly into so called normal modes of vibrations, which form bases in terms of which irreps are represented. So, if you have to calculate the intensity of a particular transition, it will amount to finding out the weightage of a particular representation that is contained in the particular vibration that you have. Okay. So, if it will sound vague right now, I am just going over it quickly, but that is what it boils down to. So, you can decompose motions. Ultimately, there is some intrinsic linearity. The vibrations are small. If there are large vibrations, then there can be non-linearity, but usually the effects that human beings can cause are small until laser science arrived. Lasers can cause non-linear effects at atomic level, but otherwise all the electric or magnetic fields you can produce are so tiny compared to the intrinsic forces, electrical and forces binding the atom, that you can only make very small disturbances. So, they can be analyzed as just linear vibrations. You can treat it like a harmonic oscillator in a general sense. So, linearity applies. And therefore, most of chemistry can use this kind of linear representation theory. Okay, so we come to this Schur's lemma, and I remember that we were doing these statements about so called kernel of a map, and I think this proof is probably the most abstract one that we are going to do. Probably this Mildred Dresselhaus's book has a better proof, but since I have not prepared for it, I will just tell you what is from Hassani's book, which is easier to, which is at least neat, it is clear. So, we had defined, so towards Schur's lemma, the first thing was to say something about kernel of linear maps. So, first of all, the definition was kernel of a map T for T which is a map from V to V prime or V to W, let us say, is all elements V. So, how should I? So, kernel A consists of V belonging to the vector space V such that T of V is 0 vector. Is the 0 vector of W. So, whatever is mapped into the 0 vector is that set in the original set is in the domain set is called the kernel, and one of the immediate results is that for a linear space the 0 on the other side is always in the map. So, for a linear map is always in the range. So, right, always the image of okay, otherwise the linear transformation properties will not work. You have to add. So, you know that adding a 0 vector doesn't, 0 is like the identity element, and so if on this side if you add 0 it shouldn't change the vector, then the image also shouldn't change. So, on the other side also you have to have this. So, that is a very simple and obvious fact. Then the next thing we were trying to prove was that a linear transformation is 1 to 1 if and only if its kernel happens to be the 0 vector. So, in other words, after all, if it is 1 to 1, then it should take only one element into a specific element, and we already have this thing here, this statement here, which is a little, I am leaving it out, it is a little obvious. So, this in this case it is, we are trying to state a bijection, I mean if and only if statement. So, not only does it map 0 vector into 0 vector, but conversely if the kernel is 0 vector, then the linear transformation also has to be 1 to 1. So, the if part is sort of clear, sorry, the only if, that is this we have already proved. And then to prove the forward statement that the map has to be 1 to 1 if the kernel is only 0, then note that if we have two different elements, not if, so for two different elements V1 and V2, so suppose that V1 and V2 are mapped into the same element on the other side. What we want to prove is that that implies that V1 must be actually equal to V2 because it's a 1 to 1. But then we know that the kernel of T is 0. So T V1 minus T V2 equal to 0 on the other side implies that V1 minus V2 is also equal to 0 because the kernel is V1 minus V2, right. So, it implies that T of by linearity in other words this has to be essentially 0 of 1 because that is the kernel. So, if it maps into 0 then this vector has to be 0 vector, that means that V1 equal to V2. So, if image is the same, the domain elements are also the same, and so that proves 1 to 1. Now, this we are going to use, this lemma we are going to use for Schur's lemma, and as I was trying to tell you, Schur's lemma should actually have been called a theorem, but I suspect that he proved it along the lines of proving the great orthogonality theorem. So, since the wonderful orthogonality theorem, so because that is the bigger theorem, people call this previous result a lemma. So, what is Schur's lemma? So, the statement of Schur's lemma that I may have written last time, we have to emphasize that it deals with irreducible representations. Such that they define irreducible representations and if there is a operator A which so here the T prime is on V prime. So, the carrier spaces are different. GL just means the general linear group, it means the some matrix representation, and V and V prime are vector spaces of potentially different sizes. They are not the same vector space. So we are trying to realize the group in two different ways. We have one carrier space V on which the same size, so if it is size n, then n by n matrices can act on it, or there is a V prime whose size may be n prime, and there will be n prime times n prime size matrices acting on it. That would be called a map T prime of all the elements of G into those matrices. So, and if there is now an operator A which is from V to V prime, which satisfies A T of G equal to T prime G of A for all G belonging to G. So in simple language, what we are saying is ultimately, although we are writing this as maps, they will become some representations d alpha, d beta. If I have two sets of representation matrices for the same group, and then I find some n by m matrix which quote commutes with, so if it is applied to representation alpha, it produces d beta times a on the other side. Such A has to be either trivial, I mean it has to be 0 or identity. That is what it shows. So you can think of it another way. You can try to apply A inverse on this side, flipped. There is no way of converting an alpha representation into beta if they are both independent irreducible representations. That's what it means. Some kind of similarity if you seek a similarity transformation like A, that doesn't, I mean it's trivial. Either it's just identity element or it is actually 0. There is no way of doing it. And that is actually what is the significance of an irreducible representation, that you cannot convert one into the other by multiplying it by some. So given an n by n representation, you will not be able to find an m by n operator acting on it which will convert it all magically into m by m representation. That will become a representation. That is the meaning of this statement. So let me just very briefly say, loosely speaking, so I didn't complete the statement. So if such A exists, then such A is or A is identity. And T prime are essentially the same. Okay. Or 0 or so loosely speaking, d alpha irrep can't be converted into d beta irrep using a linear operator A of size alpha beta. So, well, beta alpha in a sense, or I should have written A beta alpha, something like this. Right. So, you have to of course make sure of the domains and ranges, but you cannot if I flip A, it will become an alpha beta kind of operator. So I can always apply beta alpha on d alpha and A inverse on the on this side and expect to get a beta size matrix, but such conversions are not possible. Okay. So and that is what leads to that orthogonality. It basically means that the representations contain completely independent vectors, the irreducible representations. So now the proof is somewhat technical. First, it observes that if a vector A belongs to kernel of A, then all Tg acting on A also belong to kernel of A. So we are trying to, so if everything belongs to kernel of A, it means that A is mapping everything into 0. Belonging to the kernel of A means it's being mapped into 0. Such things in linear transformation theory are done only by 0 maps, taking a whole space and converting it into a 0 on the others in the range from domain means that that is essentially a 0 transformation. So we are moving towards that. So this can be seen because so let A belong to kernel of A and we take A acting on Tg of A, but that according to the hypothesis should be same as T prime G A on the other side on A, but that means that since this is A of this is 0 because it's kernel of A, so this is equal to 0. That means that A belonging to ker A implied that T after applying Tg also it continues to belong to ker A. Okay. Now, if T is an irreducible representation, then either it is a trivial map, which means that it will send either it is going to send all of V into one element, the 0 element, or it should not do anything to it, or the ker A has to be 0 vector. So I call this result star for the time being, a statement star and star. So these are the conditions for T being in an irrep, okay, and star would mean that A is essentially trivial, A is 0 map, and if it is 2, then it means it's a 1-to-1 map. This is where we are using that lemma. So the strategy is to prove a map to be both injective and surjective. That makes it 1 to 1. Okay. And in both cases, it is the first option that will work out. In both cases this will happen, and so the first is what will happen, and so we'll essentially see that A is 0. The reverse part basically now starts from the other side. Part 2, let B belong to A of V for example equal to A of some x with x belonging to V. And now we start with, because this is in the A, remember, is a map from V to V prime. So this B actually belongs to V prime. Now we want to use that condition that A commutes with T and T prime. So T prime G acting on B is equal to T prime G A of x, that is the line above, B is equal to A of x, but this we can write as equal to A of Tg of x. But that means that this also belongs to the image of A. So Tg of x also is something that belongs to A of V. Now again we remind ourselves of the properties of what is an irrep. That T prime is an irreducible representation implies either that A of V has to be 0 or that A of V has to be equal to V prime, all of V prime. And we put some symbols here to tally things, call this statement this and this double dagger. This is what I chose once. So now this and this are essentially same, that kernel of A is all of V, all of V is demolished by A, and this is what this is basically saying. So whereas if it is 2, then it means that A is actually surjective. Thus we see that A is both surjective and injective, and A which satisfies the condition of the lemma that A T is equal to T prime A. If such A exists, then it is both injective and surjective. So, either it is an isomorphism, which means essentially an identity matrix kind of thing, or of course, it can mean that T and T prime are equivalent, but we will see that that is not real. I mean, the T and T prime will actually be the same in this case. So, and this means that A is either an isomorphism or A is just 0. A which was from V to V prime, including the case 0, well, I shouldn't say including because 0. So, the role of an A which quote commutes with, I mean it or quote purports to convert a map T into T prime has to essentially be either do nothing unusual or has to be just 0 if it is tries to do something unusual. So, that is the proof. I suggest that you study it a bit. If you have a question, we will discuss it again later. But this is a formal proof and you have to spend a little time thinking about it. Okay. So, this is the end of proof. And actually lot of people, so proving that it is identity can be a few steps more to check that if T and T prime are same, and A Tg is equal to Tga, then such A is proportional to identity. So, we will skip these steps. We have seen the crux of the proof, most of it is that, and it can also be proved by by an extension of those, that reasoning, and specializing to the case when T becomes T prime. We can actually check that it is identity, because in that case it cannot be all 0 and it is bijective and injective. So, it will be essentially equal to identity map up to a constant.